Yeah, so I'm going to talk about Lakehouse systems, so more like the technology you use for data processing and machine learning, and talk about how this is sort of a new design for these systems that has a lot of exciting possibilities. So it's a trend that's been happening throughout the industry. Databricks is one of the pioneers in this space, but quite a few other companies have, either internal tech stacks or sort of products that are based on this architecture. So I want to explain, what it is and why it's interesting. So in brief, basically, what I'm going to talk about is that many of today's problems that users have with data and AI stem from the complexity of the data architectures that we use. And it is possible to simplify those. And if you do that, it's actually easier for all kinds of people in your organizations to work with data and AI. And so Lakehouse systems are one step towards this that basically try to let you do a variety of workloads and get a bunch of powerful data management features directly on like really large scale data that you have present in data lakes. Little bit about Databricks, if you don't know about it. We're a data and AI platform service in the cloud that just runs over the three major public clouds with about 7,000 enterprise customers. And we provide a platform that supports, a range of data and AI workloads, all the way from ETL and data science to machine learning and SQL data warehousing. And we're used in a whole bunch of domains across the industry. Here are some of them, but basically all of them involve some kind of large-scale data processing, and then either business, intelligence style reporting, or machine learning and data science on these very large volumes of data. So as we talk with all these folks in industry, like we are always asking, what are the biggest challenges that data users have in your company? And the interesting thing we found with all of these is that many of these challenges are usually about the data itself. That's actually the primary thing. So let me explain what I mean. So in particular, we see three big challenges coming up. The first one is just access. Can I even access this data, like for my job? Or is it too hard to get access to the platform or to connect it to the tools that I want to use? Like say, as a data scientist, I want to use PyTorch or something to train a model on the data or whatever it is. So obviously, if you don't have access to the data, you can't do anything with it. It's a big problem. The second one is reliability. Data quality is a huge issue. If you have access to data, but it's incorrect, or it takes months to fix an issue in it because some other team has to change something, that's a huge problem. And then the third one is timeliness. If you don't get to use like the newest data, if the data you're working with is weeks or months old, that's also a problem for many use cases. So we're not the only ones to see this. For example, this is a survey that Fivetran did of data analysts across a bunch of organizations. And they found that the top challenge that was reported was data quality by 60% of the respondents there. And also, they found that 86% of them had to use stale data, 40% had to use data that's more than 2 months old, and the vast majority regularly had some unreliable data sources. So these are the top issues for them. It's not like specific features of the platform they work on, does it have this function, is this aspect fast or whatever. It's actually, just the data itself is wrong. And the same thing is true if you look at data scientists. This was a survey from Kaggle where they found that data scientists spend most of their time analyzing and understanding data, and then also quite a bit of time just trying to build production versions of their data and AI workflows. So one thing I want to call out here, so obviously getting high quality and timely data is hard in itself. No one says this is going to be easy, but part of it is actually a problem of our own making because of the way that a lot of organizations, design their data infrastructure today, and just because of the history of the different systems available to do this stuff. So let me explain what I mean. So let's go back to when analytical data systems started, which was in the 1980s with data warehouses. So at this point, many organizations had started using computing in various ways, and they have these operational databases like the say ticket reservation system on an airline or something like that. And they wanted to analyze what's happening in them. So the initial idea of data warehouse systems was you can take all this operational data and then extract, transform, and load it into into a system that's designed for fast analytical processing and organize it in a way that's good for that. And then on top of that, you would then have people run business intelligence or reports or whatever. And these data warehouses had a lot of powerful features for management and for performance. Things like schemas, indexes, asset transactions, all kinds of stuff like that. And obviously, they're very successful and still widely used today. Now, the problem, though, is that in more recent years, we started to see a lot of use cases and data types that aren't well supported by data warehouses. So first of all, they couldn't really support unstructured and semi-structured data that well. You can load it in there, but it's clunky to work with it, and often it's also very expensive because this data is much larger. So things like time series, logs, images, documents, and so on. The pure SQL model had a problem with. The second one is the high cost to store large data sets. Even structured tabular data, at large, you can collect it at very large scale today, and it becomes expensive in a lot of these systems. And finally, they didn't support data science and machine learning, which increasingly organizations, were figuring out how to use and getting a lot of success with. So this led to this second kind of system entering the picture that's often used together with data warehouses, which is data lakes. So the idea there is you have low-cost storage that can hold any type of data. It's not just restricted to tables, and it's just designed so you can store everything you need and then process it later. And so this is usually organized around the file interface. So something like Amazon S3 or Hadoop file system, or like all the different cloud storage systems out there. And another interesting thing about it is that in these file system based kind of platforms, a lot of the ecosystem settled around open data formats, such as Apache PECASE, which are directly accessible by a whole bunch of machine learning and data science engines, in addition to SQL engines. So you have all this ecosystem of open source software or commercial products out there that all know how to read the data in your data lake because they understand PECASE format. And that's made it very attractive for running these workloads in there, because new algorithms, new libraries come out, every year that you may want to use for data science. And then, you've got the majority of the data in the data lake. But if you want to do the traditional reporting and have really great experience with that, or if you want strong management features like fine-grained access control and transactions and stuff, you can always load a subset of it into the data warehouse, and then you can do all that great stuff that's existed for 40 years in those systems. So you have just ETL jobs. And still, the vast majority of data in most enterprises ends up just living in the data lake, and then like subsets get loaded into the warehouse to do other stuff. So when you look at this, it seems like, hey, maybe we've solved the problem. You can now store all your data, deal with all these, weird new types of unstructured data, and still get the benefits of, what the data warehouse used to do. But there's a crucial difference and kind of a step back from the initial data warehouse vision, which is that the two-tier architecture is very complex. And this is one of the things that causes a lot of problems for people in practice. So one of the problems is with this two-tier architecture, data reliability suffers a lot. You've got the multiple storage systems you have to think about, at least the data lake and the data warehouse, maybe also things like message queues in between, like Apache Kafka or something like that. And they each have slightly different semantics. Maybe slightly different data types, and you also have all these jobs that have to move data between them. And if any of those things goes wrong or has a bug, you're going to get, low quality or like missing data downstream. So that having these many systems involved that the data has to move through before it gets to your user, it really hurts reliability. Second problem is with timeliness. Again, the more steps, the more systems your data has to flow through before an end user can actually use it in their BI tool or in their data science workbench or whatever, the more delay that adds. And that's what leads to these very long delays and slows people down. And then, of course, you also have higher costs because some of your data has to be duplicated into multiple systems, and you just have these pipelines that are always running that are basically just copying data from one place to another. They're not really doing useful work. So that's what Lakehouse systems try to solve. And the idea there is, let's not have these two tiers anymore. Let's instead try to make the data lake better. And let's try to implement all the management and performance features that are required for data warehousing on top of this data in these open formats. And if you can pull that off, then you get a picture like this, where you can put all your data in the data lake. You can still get the very low-cost storage you'd get from something like S3 and use open formats. And you can have this layer on top that does management, access control, and various things to optimize performance. And on top of that, you've got two interfaces. You've got a SQL interface that looks like a data warehouse for all those SQL workloads. And you've got this direct access interface for all those open source tools that just want to crunch a lot of data themselves, like TensorFlow or scikit-learn or whatever. They can just directly open and work with these files. So that's kind of the picture. Of course, the question is, can we get great performance and governance and all the other things we need with this design? So a bunch of organizations in the industry have been making this happen, and it's increasingly possible to do it. And I want to talk about three technology trends that are enabling this, that various companies are kind of developing in parallel. So the first one is metadata layers for data lakes. This is the layer I showed in there that adds various management features on top of this data in an open format. The second is Lakehouse specific SQL engines, which are actually getting really great SQL performance even in this data lake environment with open storage formats, which is very different from traditional engines that assume that they control the format exactly. And then the last one is declarative interfaces for data science and machine learning that make it even easier to run these kind of complex advanced analytics workloads on top of the Lakehouse. Okay, so let me start with this first one. So the idea between these layers inside these layers is actually pretty simple. Basically, you've got your data lake, which at the low level it's a collection of files. That's how things are stored inside it. But you want it to look like tables and like something more like the data in a data warehouse. And the idea is, in this metadata layer, we're going to track which files are part of each table version, and we're going to interpose on all the requests from client applications, so we can implement management features like, say, transactions where you change a whole table at once, and governance features like access control where you decide who can get to which data. And then once you talk to this layer and you authenticate to it and like you figure out you have access to something, the client can still read the individual files at high speed and can get great performance on those. So a bunch of open source systems have been driving this design. At Databricks, we started and released Delta Lake, which is probably the most widely used in this space. But at roughly the same time, Netflix developed Apache Iceberg, and Uber developed Apache Hudi, which are two other systems that follow similar design. And so these companies are actually like using these systems as the main way they manage data inside there. So I'll just give you a short example on how these work and how they help make the data lake much easier to do workloads on. So first, let's imagine you just had a traditional data lake and you stored your table in there as a collection of files. So this would be something like Apache Hive. It's great if your data never changes. You're storing it, it's really low cost, and it's awesome, and you can just read it and do queries on it. But there are a lot of problems when you start having many concurrent workloads on this data. So for example, one of the things that's hard in a traditional data lake is having transactions. Let's imagine we want to run a transaction like delete all events about customer number 17. What we'd have to do in the data lake is to rewrite, all the files that contain stuff about this customer. So maybe file 1 here, and then delete the original. And we also want to rewrite maybe file 3 and delete the original so that we get a table with all the right data. But what if there's another query running, that reads the table while this delete is running? Is going to see some weird intermediate state that's inconsistent. So it might see, for example, file 1 and file 1b at the same time, so it will see duplicate data, or it might see, that some of the records about the customer were deleted and some weren't. So this is, one of the things that makes it hard to do traditional data warehousing on top of data lakes directly. That's why for a lot of organizations, they're mostly kind of an archival and ETL storage system. So how does a system like Delta Lake solve this? The idea is really simple. Is we're still going to have the data in these raw files, but we're going to maintain a transaction log, which is basically a data structure that a lot of database systems use internally, that tells us which files are part of each version of a table. And this allows us to kind of move the whole table through new versions in time atomically, so that everything moves all at once. So as an example, we've got this table here, and let's say we want to delete all the events about customer 17. Well, what we do is we would rewrite these files. You would rewrite file 1 and file 3. And at this point, no one is actually seeing the new files, because when they look at the log and they ask, hey, what's the latest version of the table, they see v2, which has the original files. And only after we're done staging all the changes, we can add a new log entry, which says, hey, the third version is now actually these new files together. And then clients will see all of the changes at once. So this is a simplified picture. There are a bunch of optimizations too, so that each log entry is sort of a change from the previous one instead of being a snapshot of the whole table. But this is the core idea. And this makes it really easy to have concurrent workloads that modify and read the table without clashing with each other, and also to have time travel back to see what did this table look like a week ago, and to do a whole bunch of other powerful features too. So here are just some of the other things you can do with it. You can do time travel. You can easily reconstruct what the table looked like sometime in the past, which is really great for debugging and fixing problems. You can also do zero copy clone. So you can create a new version of the table that starts off at some old table and only remembers the changes, which is really great for development and testing. You can see the history of everything. With these layers, you can also guarantee that the history can't be tampered with for auditing. And you can also we actually also keep track of the schema you expect and constraints, and we can do quality checks before you put data into a table. And then some other cool things you can do. What we've seen a lot of customers doing is actually using these tables as message queues as well. So removing the need to have a separate message queue like Kafka when you're just moving data at high volume between different ETL pipelines. And the way that works is with, for example, with the Spark streaming interface to Delta and with the Apache Flink interface to it, you can basically treat the changes to a table as a stream. So you can listen to just new insertions into the table using the log, which tells you, just exactly when data is inserted. And you can also combine this with transactions to make sure you process everything exactly once. And then another thing that we launched last year that's really cool is support for sharing parts of your table across organizations. So we have this open protocol, delta sharing, where you basically can run a server and can give any client that knows how to read Parquet, essentially, you can give it secure access to a subset of your table. And it works a lot like what I talked about before, where basically the client authenticates, then we see which data it can access, and we give it a token to read just those files. And the nice thing about this, compared to data sharing inside a data warehouse, is the recipient can be using a completely different platform. So for example, maybe you host your table in Databricks, but your recipient is just running Spark on, say, Amazon Elastic MapReduce. That's fine. They can still share data between them. So you don't need to get like everyone to move to one platform, which is really hard if you want to coordinate across many organizations. So that's an example of this metadata layer. And in the past few years, these layers have really started to become the main way that at least our customers manage data and data lakes. So just on Databricks, this is used by thousands of companies, and I think it's around 75% of the workload in terms of writes of data. So it's a huge amount of adoption from when this was released back in 2018. And it's also got a great ecosystem of other products and open source projects that connect to it. So you can run it the same way in many environments. So that's kind of the first step, and that turns the data lake from a collection of files into something with very rich features where different teams can work on something together. But that's not enough. You also need to get great performance in order for this to keep up with data warehouses. And you also need to have really good support for data science and ML. So let me talk about the performance part next. So traditionally, in data warehouses, the common wisdom was that you have to co-design the storage and the query engine to get the best performance. And the data warehouse has to fully control all access to the storage. It doesn't want any other engines, reading or writing that data because it could somehow interfere with its performance. So this is one of the things that's made them closed platforms, because each data warehouse has a proprietary, internal format, and there's no way that, let's say, the person developing TensorFlow or the person developing Spark, like I was back in the day or whatever, can write a new computing layer that connects to that format, because like even the details are not public. So with Lakehouse, we wanted to keep the format open so that you have this broad ecosystem of applications that can all run on your data without having to copy it somewhere else. And so the question is, can you get great performance with that? And it turns out that even with a fixed, directly accessible format, which we don't control, it's just a community standard, you can actually get great performance for data warehousing workload using 4 different optimizations. So the first 2 are auxiliary data structures that you can keep alongside the data, like statistics and indexes, and then data layout optimizations inside the files themselves to group together, records that are likely to be accessed together. And these 2 things help you minimize IOs for cold data, which is data you don't frequently access. And that turns out to be the dominant factor for performance on cold data. So as long as your queries can easily find the subset of the data they need, and it's close together in files, you don't need many IOs, you're going to get great performance. And it doesn't matter whether it's like Parquet or some custom format you design, because you're ultimately limited by like how many bytes per second you can read from cold storage, such as S3. So that's one set of optimizations. And then the second one is, in most workloads, there is a subset of data, like the most recent data that's accessed very frequently. For that subset, you can cache it in whatever format works best for you. And you can also optimize execution on that format through ideas like vectorization that a lot of data warehouses use. And these allow you to match the performance of these systems on hot data. So a bunch of engines, again, are actually implementing all these ideas. And we have something called Databricks Delta Engine that's optimized for Delta Lake and does a lot of these things. So let me explain just a few of the things it does. One of them was these auxiliary data structures. So even if the base data is in an open format like Parquet, we can keep these other data structures on the side to speed up queries. And whenever you make a transaction on your table, like inserting or deleting data, we can also update these helper data structures so that they're always consistent. So for example, one of the things we do is we keep what are called min-max zone maps that help with data skipping. So for every chunk of data in the table, we keep track of the minimum and maximum values of each column in there, and then this is actually stored together in one data structure in the delta log, so it's very fast to read. And then when you're planning a query, you can quickly skip all the pieces of data that are irrelevant to that query. So for example, here, if I'm selecting events where year equals 2020 and UID is 24,000, I can just look at these and see, for example, file 1 doesn't have the maximum year is 2019, so I can skip that. File 2, the maximum UID is 14,000, so I can skip that. And then file 3 is the one that might contain this. So I can narrow down how much of the table I read. And a second example of that is just a traditional tree index. So we're also building these on top of Delta Lake. Second optimization is the data layout itself. So even if you've got this fixed open format, it turns out a lot of the performance in modern data warehouse engines comes from smartly choosing which items to store next to each other, so that when you make an I/O request to the storage, you minimize the amount of I/Os you need to get all the data that you want. And one example of that is clustering the data across various dimensions. So you can actually take a table, and if you've got two dimensions that you're querying by, say, like source user and destination user for like messages or something like that, you can actually cluster it so that records are close together in both of them. And then as long as you've got queries on either of those attributes, you get good performance. So that's one of the things that we do in Delta Lake, and it's independent of the format. It just reduces the amount of I/O that you need. Third optimization is caching. So hot data, even in a data warehouse system, gets loaded into something like solid-state disks or RAM for best performance. And you can do the same in these Lakehouse systems. And because you've got a layer like Delta Lake that knows about transactions and versions of the table, it's also fully consistent. This has a problem with a lot of projects that try to do caching on data lakes had these consistency problems, but with this you can avoid it. So this is an example of the cache that we use, which is a much more efficient format for processing the data than Parquet, that gets you really good performance on the hot data. And then the final one is the actual execution engine itself. And it turns out you can just take a lot of the ideas that data warehouses do on proprietary formats and apply them to open formats like Parquet. So for example, we've been developing something called Photon, which is a vectorized engine that uses vector instructions on CPUs that can process many items at once. And it turns out you can apply that over Parquet or over our cache format and get really good performance. Basically run about 10 times faster than the Java-based data lake engines out there. So once you put all of these together, you've got good performance on cold data because you can quickly find the data you need using indexes, and you can cluster the data together to minimize the amount you actually need to find. And you've got good performance on hot data. And it turns out that across like wide, like really broad workloads, you can match or even outperform data warehouses. So this is an example of a third-party benchmark that the Barcelona Supercomputing Center ran, comparing Databricks to Snowflake on a pure data warehousing workload, which is TPC-DS. So it's a kind of a standard benchmark designed by a consortium of database companies with about 99 queries for data warehousing, and we ran it on 100 terabytes. And you can see we were both faster and also lower cost than one leading data warehouse. So all these optimizations today mean that you can easily match, and in many cases even outperform systems that are just specialized to do this stuff. So that's the engine designs. And so the final thing I want to talk about is how this ties into data science and machine learning, and how it can make it even better than doing these things on a data lake. So first of all, like trying to do machine learning over a data warehouse can be pretty hard. The problem is that ML workloads, unlike most SQL workloads that you run, they actually want to read pretty much your whole table, or like even multiple tables, and they want to just feed it through some non-SQL code, like say TensorFlow, and crunch on it. So they're not just selecting a small amount and displaying it on the screen. And doing this over something like JDBC and ODBC is really slow. And in most data warehouses, they also have to transcode the data from their internal proprietary format to something else like Apache Arrow that these open engines can read. And that is also expensive. There's just extra work copying the bytes into a new format. So people do a variety of things. Some connect to the data warehouse directly and incur this cost. Some of them export it to a data lake, but then this adds more ETL steps that can go wrong and more staleness. And some of them maintain production data sets in both systems. And again, this adds a lot of complexity to keep them in sync. Now, with the Lakehouse, first of all, your ML engines can directly understand a lot of the data formats inside. So that's already a nice step. So basically, as long as you figure out, which Parquet files are part of this table version, you can just pass them to one of these engines and it will read them. But there are also increasingly a bunch of declarative APIs that make it easier to select data and actually take advantage of the query processing features I talked about to further speed up the data preparation for ML and the data loading. And then the other cool thing you get is with the data versioning and streaming support, you can also more easily manage your ML applications. So for example, we've seen a lot of customers building feature stores on Delta Lake where they can track exactly which version of a table was used to compute each feature and to compute each model, and they can easily debug things and roll them back. So these management, quality of life features that started in the data warehouse world are really useful for machine learning as well. So just as an example of how this works in Spark, so if you use Spark data frames to prepare and select your data for machine learning, and if you're running on top of a Lakehouse system like Delta Lake, you can get a lot of benefits. So first of all, Spark understands what your query is trying to do and actually can optimize the query plan. Then it can use things like the indexes I talked about and the cache and so on to quickly select the data that you need. And then when you train your model, you can also easily log which versions of the data you used and so on, which we do on our platform through the MLflow open source project. So you can easily then go back and see exactly what went into this one training run of my model. So that's kind of all the pieces of the Lakehouse. So if you put these together, basically Lakehouse systems try to combine the benefits of data warehouses and lakes, but even more importantly, because they reduce the amount of different systems and steps that your data has to go through, they're often sort of greater than the sum of the two parts. So first of all, you've got open interfaces, so many tools can talk to your data. You've got these rich management features like transactions and versioning, and you still have good performance for the SQL workloads, and you have low cost, which is the same as cloud storage for the data that goes in. You're just paying S3 or whatever. You don't have to duplicate it or to pay a higher rate because you're going through a data warehouse vendor. And the really important thing, though, is that once you have more and more workloads that talk to basically the same copy of the table instead of waiting for it to be moved around, you can really simplify your data architecture and improve access, reliability, and timeliness for all the users, because they can all go in and query like the new data exactly as it arrives, like they used to do back in the original vision for data warehouses without all these steps in between. And so this leads to a lot of organizations really simplifying their architecture. This is just one example picture here where on the left you have a whole bunch of systems. You have message queues, tables in the data lake, data warehouses that different people use. And on the right, if you put them all in a lakehouse system, you just have to worry about delta tables basically, and you can, all of these things can safely connect to them and work with them, and you've got a lot fewer of these steps between them. So that's mostly what I wanted to talk about. I think I have time for a few questions too, if you have any. So thanks.
Great, thanks, Matei. That was a wonderful presentation. It looks like we've got a question right now from Shabazz, and they are asking, well, first off, they said, nice presentation, Matei. The question is, during parallel processing, can the order of the transactions be impacted?
Great question. Yeah. So with Delta Lake, that can't happen. So they're always serializable in sort of database speak. And the way that works is that we designed the process for appending to the log. So only one client can ever append a specific version number. Like if I'm writing version 3 and you're trying to write version 3, only one of us can win. Now the other client can still retry later, so they'll still end up in some order. Yeah.
Okay, great.
Awesome. I'll come in here with a question myself, and yeah, feel free to keep on asking questions in the chat. So I have to figure out how to ask this properly, because I've got to make sure that I understand things properly. So is there any need for Delta Lake to do any rewriting of the Parquet files if there's hot query paths that because I imagine you say you've got a large number of Parquet files, and for whatever reason, the data that you want to query is distributed across a large number of files. And you've got to read 1,000 Parquet files or 10,000
so
Parquet
you
files.
want to regroup them.
Yeah, does Delta Lake do any rewriting or regrouping to support hot query paths, or is Z clustering enough to kind of achieve those ends for you?
Yeah, that's a great question. Yeah, it can. Yes, it can actually regroup stuff and recluster it even to optimize performance. And so there's this optimize command you can run on it that does a few things. That can cluster the data if it's not already clustered, and that can also deal with if you have a lot of small files because you were inserting a little bit at a time, it can coalesce them into a big one. And then the other thing I didn't talk about here is sometimes you go back and let's say you want to delete a bunch of records or something. It also can support efficient merge operations where you see what was deleted and then you rewrite things to get rid of those. And the cool thing is these can all happen in the background while other transactions are running, and they can just kind of add their own transaction and swap some of the files with others. Yeah, so we have a bunch of features that do that, and we're also basically a lot of these are open source, so you can just kind of run these on there. Yeah.
Awesome, cool. Looks like we got a few more coming through here as well. Let me just
great. So we got a question here from Nancy Matei. She says metadata layer covers part of the data governance functions, but how about data lineage and data mask?
Yeah.
She also asks, can Data Lakehouse integrate with other data governance tools like Data Hub?
Yeah, great question. Yeah, so I didn't talk that much about these. So for data lineage, yes, there are a lot of tools that integrate with this already. So I believe Data Hub already supports, for example, Spark and Presto workloads. So it can, and then it doesn't matter whether you're reading from Delta Lake or other formats. It will be able to collect lineage. On Databricks, we also have a built-in lineage product that's in preview right now, but that also supports that. And for data masking and access control, I didn't talk much about it, but in that layer in front of the table, you can also do that. So for example, you can say, hey, this person doesn't have access to this table, so I'll reject the request. Or you can even filter the data and give them a filtered file. So again, on Databricks, we have something called Unity Catalog. That's basically an operational catalog that can do fine-grained access control on top of this data. And other organizations are also building their own, like Lake Formation's an example from Amazon. There are others like that too. Yeah.
Okay, great, awesome. And we've got a follow question here from Pratik, who asks, does Delta Lake throw out the traditional data modeling practice?
Yeah, great question. We don't think it should. I mean, we think the way you model your data and then like the system you use that runs that actually runs the commands and manages the data are like slightly independent. Yeah, it's a bit confusing. Like when I talk about architecture or platform, well, I try to avoid the word architecture for that reason. But when I talked about platforms here, I meant more like, hey, the engine underneath. I think the traditional data modeling practices make a lot of sense, and we see a lot of people using them successfully in this world. One of the new things you can do here that maybe was harder to do traditionally, although some data warehouses do it, is it's also easy to have development workflows where you clone something and like work on a copy and then throw it away. So some people are kind of tweaking their workloads for that reason. Like maybe you stage a new copy of a table and then like you run some tests and only start using it later. But we think, yeah, you should be able to use these.
Okay, great.
Awesome. Sorry I removed you, Matei. So I also saw that you, I'll have another question as well. So I saw that you included a performance benchmark comparing with Snowflake on there as well. And unless I'm mistaken, kind of traditionally, maybe Databricks and Snowflake have kind of taken on separate domains, but it seems like maybe there's a little bit more crossover in recent years with some of the new products. Maybe you can speak a little bit to, as Snowflake is another kind of competitor that's looking to, challenge some of the traditional data warehouses. Maybe you can speak to your interpretation of like how these two systems play, and do you think that you need both? Maybe choose one or the other. What's your take?
Yeah, no, yeah, they are ultimately pretty different products. So I think that was just to show that the data warehousing part, can be competitive, and that's an example of like a well-known warehouse that we tested against. We also test against others like regularly to make sure that we're doing well there. But yeah, they are different. Like right now, I think so. First, I think if you want like really powerful warehousing features, there are a lot of things in these dedicated products that are that are ahead of like where some of these lakehouse systems are, just because they started earlier. So you may be more connectors to different kinds of tools and so on, and maybe more built-in functions and so on. But I do think that the lakehouse type of design is showing success in a lot of places and is catching up. And we're not the only vendor that does that. Like there's stuff like Starburst, for example, for Presto. There's like Athena and BigQuery are starting to do things like this. So we're not the only ones that are moving in this direction. So I do think in the long term, like these types of systems will converge a little bit. But today people still do use a mix of things, and it's fine. And like we also have great stuff on connecting to Snowflake and moving data between the two and so on. I'm just saying, like from 10,000 feet, it's I don't think there's like a technical reason why you would need to have two systems in the long term once these things converge. But yeah.